I would like to ask you whether you can check for the lunch. Once again, I will show the slide, or probably not. Have you been able to connect to the internet? No. So I will, before that. Yes. Before that, sorry, I will just hop in and I will show you how to do this. Yeah. Okay. But before your presentation, I will just show others how to connect to internet and make lunch selection. Okay. Few minutes.
That's okay. So the 5 minutes you can have.
Yeah.
we suddenly, how can I say, catch up with the original schedule.
So depending on your operating system, like SSID is VUT Brno, and it is without any encryption. And as soon as you will try to associate yourself and enter some web page, you will see a captive portal just like this. And over here, put OMNeT as a username, and password is Starobrno. It should lead you towards the page. And using this, you should be connected. Yeah. And after this, please visit as the first thing the web page with the lunch selection. There are already 11 responses, but we will need at least 10 more in next 15-20 minutes, so we can have a huge order by supplier, because it's around 22 attendees right now here, and they urge us to make selection and make order as soon as possible so that we will avoid a lunchtime rush hour. So that would be all from me. I hope that finally you are connected. Not you, Antonio. I don't know why. And I will. Yeah. OMNeT as username, Starobrno as password, this web page. And SSID was boot Brno. Okay, so I will hand it to the Marco. The seat is yours.
Okay, we have our third speaker today, is Marco Tiloca, together with Alexandra Stagkopoulou and Gianluca Dini. The title is Performance and Security Evaluation of SDN Networks in OMNeT++, INET. So let's give Marco Tiloca the clap, please.
Thanks a lot. I'm not a purely OMNeT++ guy. I work on network and communication security, and I've been using OMNeT for a while now for the sake of our research projects on security. So, software-defined networking have been recently introduced mostly for trying to make it easier and more flexible to configure, reconfigure, manage arbitrarily complicated network scenario, and it relies essentially on one key concept: the distance separation between control plane and data plane, where control plane addresses the actual management of traffic routes by generating and installing them on very simple and straightforward switches devices, while generating them on an omniscient central SDN controller. The data plane instead is about the actual handling and forwarding of network packets, thanks to very simple switch devices that just check for matching in their local flow tables before forwarding network messages. And over time, a lot of standards have been developed in order to provide APIs and common control messages for communication between controller and switches, but nowadays essentially OpenFlow has become the de facto standard for that. This is just a simple example of flow establishment and packet forwarding in SDN. We have a host A that wants to send a packet to host B. The packet, first of all, reaches the switch that doesn't know what to do with that, contacts the SDN controller to receive instruction, and a flow, to put it simple, is established on the switch. So from then on, the switch, to make it simple, knows what to do with packets coming from host B to be delivered to host B. Essentially, it simply follows the policies installed and possibly updated by the controller and stored in its local flow table. But having said that, we found, I'd say, a gap in what is evaluation of a number of things in SDN networks especially. It would be nice for a network designer as a final user to evaluate quantitatively a number of things far ahead before deployment. So at design time, well, you can do that with some kind of analytical models maybe, but most likely it's very difficult unless you would like to introduce some oversimplifying assumption. So of course simulation becomes quite an obvious choice. What could you be interested in evaluating? Three things, I'd say. Classic performance indicators people usually tend to consider in network evaluation, so throughput, delay, packet loss, and so on and so forth. I would say also the behavior of particular SDN-based monitoring systems as additional application running with the controller and responsible for analyzing network communication, detecting anomalies, and possibly mitigating them. And you would like to evaluate the services as to their effectiveness and reactiveness and accuracy in detecting anomalies and mitigating them. And third, and this is honestly the thing we care the most because we are security guys, evaluating the impact and effect of successful security attacks carried out against the network. And this would definitely help to rank attacks based on their severity, and then that would further help to possibly select the best countermeasures to adopt for them. So our practical goal is to build a simulation tool based on OMNeT++ and INET that essentially enables the evaluation of the three things I've just mentioned. This is currently work in progress. The source code is available on GitHub, but we are working on that as we speak. I'm going to go into a little bit more details on the three things I've just mentioned, but just to make it clear and draw a clear line here, this tool is not about discovering new attacks and vulnerabilities, and it is not about evaluating feasibility and likelihood of success of security attacks. It's just to quantitatively assess their impact if they succeed. So the first thing, as I said, is adding actual support to SDN to INET, essentially. I mean, we didn't start from scratch. That was quite a good starting point, released 3 years ago, a software module by some German guy in the paper cited at the end of the slide. We started from that essentially to extend what was just a basic support for SDN controller and switches to support additional OpenFlow messages for flow establishment and update, collection of statistics from switches, and an arbitrary complex packet matching on the switch devices. As further extension, we are going also to consider additional, more complex techniques for statistic collection from switches like S-flow, rather than the basic OpenFlow-based approach, and additional modules supporting commercially available application service running on the controller. Just to give you an architectural idea of what means bringing SDN into INET, well, the SDN controller is relatively easy. It's just another host running a traditional TCP/IP stack. It's just that on top of that, you have a specific controller application, or I would say collection of applications responsible for a number of things like establishing, updating flows on the switches, or, as I say, that particular class of applications for network monitoring. Things become a little bit more complicated when you consider a switch, because at the same time, on the same physical unit, you have on one hand the control plane. Well, that's yet another traditional host with a traditional stack to interface the switch with the controller. But at the same time, sharing with the control plane the same flow table data structure, you have a data plane, which is essentially a collection of multiple MAC network interfaces connecting the same physical layer, of course, with one single forwarding application instance, interacting with the flow table to understand, okay, this packet has just come through this MAC interface, I'm supposed, according to this flow, to redirect it to this outgoing MAC interface for delivery. That's it about SDN's actual SDN support. As I said, it's good to consider also specific application services on the controller. To this end, since we are again mostly interested in evaluating the impact of attacks as main contribution, here we have implemented really the basic methods one can think about as a proof of concept, but of course one can consider to implement additional modules mirroring and providing a service actually available online and on the market. But at the end of the day, whatever choice you do in particular, it's about these three steps. You're supposed somehow to collect statistics from the switches, to analyze them according to a number of techniques possibly combined together, especially analysis of overall traffic anomalies based on threshold approaches and entropy-based analysis, and analysis of packet counters both from and to network nodes in order to try to detect anomalous traffic volumes. If you detect something that is wrong for you, you're supposed to try to mitigate this anomaly, for instance, trying to isolate the suspected source of anomaly or attack. In the end, trying to install or update flows on the switches and apply some, for instance, drop policy on incoming packets. Third and most important for us thing, again, is the evaluation of the impact and effects of security attacks. And I stress the word effects here. We assume that these attacks we evaluate have been successfully performed. So we don't care about reproducing, simulating, emulating, and all their actual performance and execution or the behavior of the real adversary. We only care about the final effects that in the end are additional events injected at runtime during the simulation. And then we assess in the end what changes, speaking of the same performance indicators in principle with respect to an attack-free case considered as a comparative baseline. The core concepts on top of which this work relies have been initially presented in the previous work last year. They are an attack specification language and an attack simulation engine, and we have been further extending them in order to support evaluation of attacks in SDN. And this practically means mostly adapting the injection of attack events on SDN switches that, as you've seen, have a much more complicated architecture to address. The first concept, well, the user is supposed to describe attacks he or she wants to evaluate in terms of effect and impact by means of a high-level attack specification language. So there's no need, again, to describe how the attack is actually executed and performed by a real adversary. You describe the list of events associated to the attack events, and you do that by using a set of high-level primitive functions provided by the language. Primitives are divided into two families, roughly. Node primitives are about the description of physical attacks targeting physical nodes and network units, while message primitives are intended for considering cyber attacks. At the end of the day, they target as actual victims the network packets themselves. This is a quick overview of the primitives currently available in the language. We are a little bit extending it now. I refer you the paper for a little bit more details, but in principle, physical attacks are described by means of a single node primitives, while cyber attacks are described by means of a list of message primitives that can be grouped together according to two possible constructions in turn. You can have conditional cyber attacks, whose list of events is actually injected at runtime during the simulation if and only if an arbitrary complex Boolean condition is evaluated as true as runtime. While on the other hand, you have unconditional cyber attacks where the list of events are injected periodically starting from a given point in time during the simulation, no matter what. The second concept is, well, enabling the actual injection during the simulation of this attack events, and to this end we developed two additional modules integrated into INET. One is the global event processor. You have a single instance in the simulator, I would say it's not really a true entity in the network, of course. And then you have the local event processor, of which you have one instance per node. So the global event processor interconnects all local event processors in the nodes with each other to enable more complex attacks involving multiple nodes together, for instance, a wormhole. Well, the local event processor in a given node is essentially responsible to intercept all packets flowing through the communication stack, outgoing and incoming, on that node, and in principle do whatever it wants on those packets. So discarding them, cloning them, inspecting or changing them, creating new packets to be injected, and so on. Hope this picture clarifies better. It's an example with two enhanced nodes. The local event processor that essentially acts as a gate bypass between each pair of layers in the stack. So again, able to intercept packets going up and down the stack, manipulating them, discarding them, or injecting new ones. While on the other end, the global event processor, as a single instance, interconnects with each other the two local event processor. This is in case you consider simple nodes, so client, server, host, even the SDN controller itself, but it's a little bit more complicated if you consider a switch, because as I said, you have two realities at the same time on the same network unit. So let's say the left part is done, the control plane, the right part is actual work in progress as we speak, because it's about actually interfacing that same single local event processor module in the switch node with all the components in the data plane. So just to wrap up how this works practically, the user is supposed to describe a list of attacks by means of the high-level attack specification language, which is compiled by means of a Python interpreter that we have developed, in order to produce an XML configuration file depicting exactly those attacks, just in an easier way for OMNeT to parse. Then you run OMNeT again, exactly the same simulation scenario without really changing anything in the implementation of any module in INET. It's just sufficient that you are sure that your INI file considers to import also that XML file into the simulation. You run in principle the same scenario, you produce some results that you are supposed then to compare with your results that you had obtained before in the attack-free case. And of course, according to your criteria system designer in your system and network, you are supposed to rank these attacks and start thinking about the best countermeasures to address them. Also, of course, during all this work, we have not fundamentally changed how INET addresses events or handle them. We have not modified any application or protocol modules in INET. Of course, if you want to, you can do that. It's not necessary for the sake of enabling attack simulation. But especially the final user, as I said before, the final user is not required to actually implement typing C++ code, an attack executional behavior or an adversary execution. The user is not required to customize, extend, implement new modules or component in INET. It just has to describe the attacks with the language, produce an XML, and run the same simulation again, in principle. So what the user needs to know essentially is exactly what he or she knows when he or she runs the attack-free scenario simulation. I have a simple and hopefully quick demo for you when I'm going to produce some of the results included in the paper, considering this very simple scenario where you have 4 client hosts on the left and 3 server hosts on the right. Essentially, they periodically send with constant rate constant size packets to the respective servers, and precisely client 1 sends packets to server 1, clients 2 and 3 together to server 2, client 4 to server 3. We have configured some simple SDN-based monitoring system applications on the SDN controller, regularly collecting statistics from the switch and trying to look for anomaly according to an entropy-based analysis approach that we have implemented just as a proof of concept to support our work on the attack evaluation. Given this context, we consider a very simple denial of service attack starting at second 90 during the simulation, where client 3, in addition to its regular traffic, starts also to send additional malevolent packets, again addressed to server 2 according to an adjustable but constant during the same simulation attack injection rate R. Now I'll show you a demo. So here we just have the simple INI file describing the attack simulation, simulation length, how the network is configured in terms of host transmission rates for the client, the application is considered, some parameters for the SDN-based monitoring system application, and so on. So as a first step, let me simply run an attack-free case just to produce some results in an attack free case that I can consider later on as a comparison baseline when I run attack. Maybe you don't see it. Yeah. Some problem with window size. And I have this here. So here select general. Yes. So let's just run this. This is simply an attack-free scenario mirroring that topology. And packets traveling back and forth. But it's quite quick. Okay. Oui. Yes. So this is essentially for each discrete second the amount of packet that server 2 receives over time, combine the packets coming from client 2 and client 3. So it's kind of constant, like you say. So let's keep this in mind as a comparison later on. Now I consider the attack that I mentioned right before. I would say it's one of the most complex to describe just because it involves the creation of a new packet. But you describe that attack like this. You have a list of nodes, it's just node 6 here, which is the ID of client 3 in the INET topology. And as you can see, if you remember already a little bit of the syntax of that attack description language, it's a single attack. And it's an unconditional attack because it starts at second 90 and then it's repeatedly performed as this list of action every 0.025 seconds, which means 40 times per second. And this is the list of action. This is our fake packet variable. We create this fake packet, you just specify its type, and this is encoded as a constant value. We have actually added, for the sake of these experiments, a new packet type in INET, but in principle you can reuse already available types. Right. So of course you need to fill its fields. Application level packets, so just payload, it's a structured payload. Here it is convenient to have the string here, track it down for the following simulation run. Then unfortunately it's INET, I have to say, so you need to be sure that you properly fill some control info parameters. They differ depending on the application level of the packet you have created, but we have some tables listing all of them. This is necessary to be sure that the packet is then injected at the correct level of the node client 3 that we are considering, and finally you just inject the packet in the transmission buffer of the nodes in the DST list with just client 3 with no additional delays. So having this description, I compile it with another Python interpreter to produce an XML file describing this attack, and I have somewhere here. Yes, so this is exactly that attack that I described before with high-level specification language, just in XML format. So at this point, to run exactly the same scenario with this attack embedded, let's say, just sufficient to specify in the ini file to import also that XML file. Then you simply run exactly the same simulation again, choosing that configuration. And starting from second 90, you should see under the name column the string my packets passing. Oh, we are not. Ooh. It's always like that with demos.
That's always the danger of live demos.
Yes.
Only one time that you need to make it operational and working.
Let me try again. Yeah, wrong path, in fact. So guys, sorry, I can show you later on and come back to the presentation to conclude it. Sorry about that. Yes, in principle, what you can produce out of that simulation is, well, the comparative baseline is the pink straight one for the attack-free case, and then you have different curves in case the attack is injected, and of course, it's quite easy to predict that, but the stronger the attack, so the higher the attack injection rate that you consider, so the number you have specified as 0.025 between two consecutive packets to be injected, result in the victim node receiving more packets during the same time frame until, and we have a good monitoring application well configured here, the attack is detected at second 120. At that point, essentially the controller installs a new policy on the switch so that all packets coming from client 3 and addressed to server 3 are just discarded. So from then on, the victim keeps on receiving only packets coming from the other client 2. If you revert the configuration and you fit the attack injection rate, you can see some changes in case you consider different values for the polling interval according to which you collect statistics from the switch. Depending on this polling interval, of course, you can be able to notice the attack happening earlier or later in time. So just to conclude, we have been working on a simulation tool based on INET that is able to enable for the final user and network designer the evaluation of a number of things on SDN networks, especially traditional performance indicators, quality on different aspects of SDN-based monitoring system application running on the controller, and final effects and impacts of security attack in the network. And to this end, the user just has to describe attacks to be evaluated with the high-level attack specification language, and it's not needed to actually implement any attack performance or adversary behavior. So in future work, we are going to finalize the support for SDN in this tool, essentially to enable attacks against switches as actual victims or more complex attack exploiting compromised switches and as attack vectors. Plus enabling additional commercially available techniques for statistical collection or SDN-based monitoring system and other services on the controller. Thanks a lot for your time.
Maybe we can have only one question because there's no time remaining for the question and answer sessions. Maybe can we just only one question? Okay, a lot of questions.
Please.
So you guys are implementing an SDN tool set or sort of framework on top of
INET.
INET. And just a clarification probably. Why do you sort of, when you look at SDN, why does the control plane also have a physical interface? Is it not somehow connected to the data plane? Because these things are sort of
in the controller.
yeah. So you have the idea that I have, maybe it's wrong, is that you have the network attachment which connects to the data plane. So, and then when something comes on that is not handled, then you call the control plane. Right. So why is the control plane again?
Because switches, it's just for the sake of interaction with the controller. So the true enforcement of the control plane is of course on the controller, but in the end it becomes pretty symbolic controls.
So you mean the control plane also has information going back and forth
On the switches.
because
Yes.
okay, supposing that the switch resides somewhere else, the controller itself resides somewhere else.
Okay, the controller is supposed to install or update new flow on the switch, and it's talking about control plane.
Okay.
Based on those policies and control plane, the switch will passively base that, and it becomes an active actor in the data plane to forward packets accordingly.
Okay, but they would basically use the same network attachment to get to the
They need to agree. That's why the standards know APIs and
Okay, because I got confused with this, you know, you have the protocol stack, and on the control plane or the implementation, you also have the physical interface there. So that's the, but in effect, they are more or less the same thing.
Yes.
They are, I mean, ideally they are bundled together. I mean,
Yes.
you use the same. Okay. Thank you.
Okay, yes.
Thanks
So
a lot, everyone.
question discussions can be done during the coffee break. So